Here, and we're going to continue this problem we were doing yesterday. Did we calculate the density of the methanol? Okay, let's go ahead and write that down. What did we get as the density of methanol? 0.79. Actually, it was more. It was like 1.3. What did we get? It was more, and then we rounded it to 4 sig figs, correct? What was it before we rounded it? Someone have it written down what it was before rounding? If you don't write it down, did I say this yesterday or the day before? If you don't show me the rounding step, I deduct points. And so you have to get in the habit. I know a lot of people are in the habit, they just read it, they look at the calculator and just round it in their head and write it down, right? But I want to see what the calculator entry was, and then I want to see how you rounded it. And so make sure you write down the pre-rounded version and then the post-rounded version for me to see. Otherwise, I take off an RO. You might see this on your exam, RO minus whatever. That means round off. You know, you didn't show me a rounding step, or you made a rounding error, something like that. RO. Or I'll write down show rounding. And so get in the habit, you know, this could be the final answer, that's fine. Oh, is this where we ended yesterday, or did we make it any farther? All right, let's go on to the next question here, number 79. If the pycnometer of exercise 78 is filled with ethanol at 20 degrees C instead of methanol, the observed mass is 33.470 grams. And so we're going to fill this with methanol, and we're going to get a different mass here. And so let's go ahead and calculate the density of ethanol based on this data. Now, what is the density of ethanol? Well, the density of ethanol is just the mass of ethanol divided by the volume of ethanol. And the volume is given by the pycnometer. The mass of ethanol is 33.470 grams. But this isn't just ethanol. As we saw, this is a pycnometer plus ethanol. And then we subtract the mass of the pycnometer, which is 25.601 grams. And then we end up with the mass of the ethanol. And so the mass of the ethanol is going to be what? 9, 6, 13, 7, 7. Is that right? 7.769 grams of ethanol. Okay, then we know the volume of the pycnometer. What was the volume of the pycnometer? Did somebody write it down from last time? 9.969 milliliters. And so this should give us the density here. The density will equal what? Can someone punch this out in the calculator? 7.769 divided by 9.969. 0.7793. Give me more digits.
158.
158.
792.
0.779315. Well, these are different numbers than I had this morning. Let's figure out why it's different. Well, I got the numbers from the students, so either the morning class is a mistake or the afternoon class is a mistake. So this volume, did everyone get 9.969 for the volume? Uh-huh.
That's from number 78, the 9.968. Is that
No, it's from the water. We got the volume of the picnometer. Remember we called this step, what did we call adding water? Did we have to add water first? What was the purpose of adding the water first? To calibrate. That step was called a calibration, right? And if we want good accuracy, we have to calibrate this picnometer. The picnometer has probably got some volume mark on the side, but you know, we want to make sure the volume that we have is the volume that we get. And the reason we can do that is because the density of water is known to a high degree of accuracy and a high degree of precision. What does that mean? High degree of accuracy and a high degree of precision. The accuracy is close to the true value, and precision is, well, there are different ways of thinking about precision. I talked about two very important ways of thinking about precision yesterday. And that's one of the things, you know, as far as studying goes is not just kind of memorizing what the professor says or regurgitating material. Studying, you know, you got to think about it and then formulate it in your own minds and your own words. And so, you know, the point of this is not necessarily exactly verbatim what the professor says. The point of this is, in my own words, this. And so in your own words, what is precision? Let's say. You know, at the very least, there are different levels, you know, and they call this, I don't know, they have all these rankings for education theory and all that stuff, but I'm not very familiar with it. You know, there are people who can, you know, retain the information and spit it out, but can't manipulate the information and can't really think about it beyond that. And then there are people who can manipulate the information that they're given and then spit it out in a different way, right? And so that's where you want to get, you know, what you want to do is, and this is what I did with my notes. You know, one of the things that I had to overcome was my memory isn't so good. You know, I tend to forget a lot of things. And so how do I get around that? You know, I was watching this video on memory, YouTube video on memory. And it's a Stanford professor talking at Stanford, and the dean, I think, or the director of the medical school there was introducing the speaker, and the speaker was talking about memory. And I think the director of the medical school, he said that he has fond memories of when he was taking organic chemistry, because when he was taking organic chemistry, he remembered every single page of his organic chemistry textbook. And I thought, wow, you know, that's pretty impressive to have that kind of photographic memory where you can just visualize the whole organic chemistry textbook. And then he said his memory is deteriorated with age. Well, I've never had that kind of memory, and there's no way I would have memorized or remembered anything of that level. And so, you know, when that professor was saying, read the book, chapter 3 times, I never did read the chapter 3 times, but I'll tell you, you know, before the test, you know how many times I read precision and thought about precision? Way more than 3 times. Because the way I did my studying was, I take the notes, and then I fill in the blanks, and then I make sure I clear up any confusing things by targeted reading in the textbook. If the targeted reading in the textbook doesn't clear up, you know, I never annotated my textbook. I used to annotate the textbook a lot. The only thing I annotated were my notes, and I'd annotate those all over because I'd write little comments or whatever else to help clarify the points. But if I couldn't get it cleared up by reading our own textbook like 5 times, 6 times, then I'd, you know, go level higher, level lower. Did I talk about that yesterday? Okay, if that still didn't work, then I'd go to office hours. And I'm bad because I haven't posted my office hours yet, but I'm going to do that today. But I'd go to the office hour and get it cleared up. And that way, I try to get it cleared up immediately so I had something to prepare for, because I knew my memory wasn't good. And there was too much information for my short-term memory to handle by cramming the night before. I just couldn't do it successfully. And so what I did was I would get that cleared up, and then I'd have a complete set of notes. And then every day, you know what I did every day? Every day I read my notes from page 1 to the current page. I did that every day, and it's easy to do because the notes aren't that thick. And so for the first week, you're reading 10 pages, 20 pages. By the time you get to the final, you know, the earlier pages are burned in your memory pretty much. And you're just studying the last. But the thing is, the repetition. So by the time you hit precision, you know, 5th week or whatever, you've seen it every day. you thought about it every day, and it doesn't take that much time, right? Whereas most people, they just do it once. They saw precision yesterday. Before the final, they start reviewing. I mean, not the final. Before the midterm, they'll start reviewing it. You know. But how much of a grasp do they have? All they can do is regurgitate it. They can't really think about it. And do you know what I mean? And so this is the way to that I found that worked for me. And so like precision, at least it was yesterday. So maybe you saw it once, maybe you saw it twice. And so the thing is, I just spit it out. I didn't tell you, these are two ways of thinking about precision. I just spit it out, and then it's up to you to figure it out, right? And so what can you tell me about precision? Uh-huh.
Is it the ability to get within the same range of results, the repeated measurements?
Yeah, a good reproducibility of measurements. That's good. Right. That's one. And then, what's another way of thinking about precision? What's the other indication of precision? Yeah, not decimals. We don't. How many sig figs? Those are two things. Reproducibility and sig figs. That's good. So, I forgot what I was talking about. What was I talking about here regarding precision? Oh, yeah. This is what I was talking about, precision. Water has a very accurate and precise density. So at 20.0 degrees C, it's known to 5 sig figs. And not only is this high precision, but this is highly accurate. Well, you can't tell it's highly accurate by looking at the number of sig figs, true or false. You can't tell how accurate this is by looking at the number of sig figs, true or false. You cannot tell. Maybe I should rephrase that. True or false? Or you can tell. Well, can you tell or can you not tell, based on the number of sig figs, how accurate that density is? You cannot tell. And so this has got to be verified by some other way to confirm its accuracy. Does that make sense? And so here we have an accurate and precise value of the density of water. And so this gives us a great way of calibrating the volume, because weighing, it's very easy to weigh things to very high precision and very high accuracy. Why? Because you just pay money. You pay money, you get an expensive balance. You get an expensive balance, it has very high precision, it has a lot of sig figs, right? And that balance, what do you do to that balance to make sure it's accurate? You calibrate with a, what do we call it? Standard mass, right? Good. And so this first step is calibration. We calibrate this. We can weigh it to a high degree of sig figs. Measuring volume is a lot more difficult. You can't, is it easy to measure volume to the nearest, this is tenths, hundredths, thousandth of a milliliter? Is that easy to do? Not necessarily. You have to have really ultra high precision glassware to do that, and it's not so easy. And so here, measuring mass is easy. You just throw it on the balance and you're done, right? And so we can measure this accurately and precisely, the mass of the water, and then just use the density to convert the mass into volume. And therefore we can get a pretty good volume for this. And that volume, what did we calculate? For the picnometer. Is this the right volume, 9.969?
You did a calculation here for the methanol, should be an 8 instead of 7.
Oh.
The second digit.
Oh, for the second digit. Oops. Yes. I made an error here. Okay, thank you. All right, that's the other thing. Oftentimes, for our homework, it's easy because our homework, there's the solutions guide. You can check your answer, although not all the answers are right. There's some errors in the solutions guide that you should be aware of. And so if your answer doesn't match with the book's answer and you've done it multiple times and you're sure you're doing it correctly, you could very well be doing it correctly. The book's answer could be wrong. Well, going back to this, here, sometimes we don't have the solutions guide to check, right? You know, oftentimes the solutions guide is not available, so we use different ways to try to help us confirm that we have the right answer, right? And so what were some of the ways that we could do that? Well, one is I should just double check my calculation. This is the simplest thing to do. You know, every semester I end up taking or deducting points because people miskeyed it in their calculator. You know, the setup was right, they just punched in the wrong numbers or something happened with the calculator error. They lost points because of it because they got the wrong answer. And so you want to double check your calculation. That's possible if you have the luxury of time. Sometimes you don't have enough time to double check your calculations. What else can you do to verify that your answer is likely correct? Is there anything else you could do? Well, there is. You could see, does the answer make physical sense, right? You know, if you're getting a density of 3 billion grams per milliliter, 3 times 10 to the 9 grams per milliliter, does that make sense to you? No, that's a ridiculous, density. Why? Because you've memorized some reasonable densities. You've memorized the range of densities. What is the range of densities? From about what to what? You know, there is science, learning science is not all about derivation and theory. You know, learning science, there's a lot of memorization you have to do. There's no way around it. You got to memorize a lot of stuff in order to understand it. And so repetition helps. So maybe you saw 1 gram per liter for gases all the way to about, on the high side, what's a high-end density? 20 grams for gold per milliliter, which is about, and the most dense element I think is iridium, and it's not much more dense. No. So you have some values that you can work with. And then other things, does the answer seem to be reasonable? And so what's our new density since I screwed up that? Can somebody repunch this in here?
0.78934.
78934. Thanks. Okay, then if we were to officially round this to 4 sig figs, we drop the 4, and this comes out 0.7893. Huh. What was this? Was it 9.969? Were there more digits here? 88?
That's what I have.
Did you plug in all the digits when you did this calculation, or did you do? Yeah, okay, this is called an intermediate round. We don't want to do that, and so let's go ahead and carry at least 1 or 2. So 9.9698, what was it? 8. Okay, we'll carry 2 extra. Plug this into your calculator and see what we end up with. Uh-huh.
It's actually 9.96688. The 9 was
Whoops.
rounded 4.
Oh, sorry. 688. Okay. This is what we got then. Thanks. 9.9688, which gives us a density of what?
0.78936.
0.78936. And to round this, we're going to go to 0.7894 grams per milliliter. All right, that density, does that density seem reasonable? Yeah, it's about 8/10 of the density of water. Right? That sounds about right for ethanol. If you've ever used ethanol? But we will in this lab. In this semester we'll use ethanol. So if you aren't familiar with it, you will be. And then we can compare these two. Which one should be more dense? Methanol, do you know the formula of methanol? Anybody? Close, CH3OH. How about ethanol? You know the formula for ethanol? C2H5OH, but I'm going to write it like this, CH3CH2OH. Which one should be more dense, you think? Should the ethanol be more dense or the methanol be more dense? You would think the ethanol should be more dense because this is a heavier molecule than this. And so I would expect the ethanol, it should be more dense because it's heavier, right? So let's take a look at the numbers here. Is the ethanol more dense? No, it's the methanol more dense. And so that might be a clue that we did something wrong, right? Maybe. Or maybe we aren't thinking of something. Is it possible that methanol has a higher density than ethanol? Is that possible? It is possible. How? How could methanol have a higher density than ethanol?
Maybe due to temperature.
Well, the temperature is the same, 20 degrees C. In fact, 78 and 79 are all at 20 degrees, 20.0 degrees C. So it's not related to temperature. It would be an unfair comparison if we did it at different temperatures. Because the density of these things vary dramatically with temperature. I'm sorry? The structure. The structure in what way? Well, actually, structure in the sense of the shape of the molecule. You know, methanol is more of a tetrahedral ball, whereas this is more elongated, right? And so, what can you pack together? If you had a box and you packed together a whole bunch of balls in there, styrofoam balls, versus styrofoam peas, you know those styrofoam. Which one do you think packs together more efficiently? The balls or the elongated pea-shaped styrofoam things? The balls. And so what we see is that this is just more efficient packing of the volume versus probably this, And so it is possible that the methanol has a higher density just because the molecules pack together more nicely in the liquid phase than ethanol molecules. Ethanol molecules have this part. In the morning, some people were suggesting the hydrogen bonding interaction is different between methanol and ethanol. And that's true too, because methanol should have a stronger hydrogen bonding interaction because it doesn't have as much of this. You know what we call this, the CH3CH2 part? We call that hydrocarbon. And hydrocarbon, one characteristic of hydrocarbons is they don't like water. Hydrocarbons are like oil. Right? And so this molecule is kind of interesting because it has this hydrocarbon part, oil-like part, and this water-like part over here, the alcohol part. And so it turns out that things like this is methanol, this is ethanol. When we start to get to something like pentanol, do you know how many carbons pentanol has? 5, or hexanol, 6 carbons. When we get to 5, 6 carbon chained alcohols, you can't dissolve them in water. They're like oil. You try to mix it with water, and it won't mix. This forms an oily film or an oily layer, and it just won't go in. And so what's happening here is, perhaps these aren't packing together as nicely. And so it could be that this is correct, But we should double check our calculations. But when we double check our calculations, we take a look at the original numbers here. And the original data here is this whole thing. The pycnometer with the methanol weighs 33.490 grams. This pycnometer with the ethanol weighs 33.470 grams. So 490 versus 470. Turns out that the ethanol weighs less with the pycnometer. And so the ethanol's got to be less dense. In other words, there's fewer atoms in the ethanol than there are in the methanol packed into that volume, right? Okay, so this is reasonable. It's reasonable that the methanol is more dense. But anyway, when we don't have a solutions guide, when we don't have the answer to look up in the back of the book, then we go through this kind of analysis to make sure we didn't make any mistakes that we might be able to correct, not lose any points. But also when you're out working, there's no solutions guide. You gotta go through and make sure everything looks correct. All right, that's part 1 of question number 79. So just a repeat calculation. Rather than methanol, we calculate the density of ethanol. Okay, now 79, there are different kinds of questions you have in science. You know, some of the questions are very straightforward. You know, they give you P, they give you V, they give you T, solve for N. You know? And so it's very simple. One answer, right? One right answer. And that's it. But when you go to things like seminars or talks or even oral examinations, the questions aren't like that. You know, the person asking the question isn't going to go, oh, with this pressure of 3.568 and this volume of 2.389 liters, you know, what is my temperature? No, they're going to ask you things like, okay, what happens with temperature and pressure? You know, when the pressure increases, tell me what goes on. You know, what are the extremes? That kind of stuff. Or, you know, tell me about volume. I'll tell you about volume. Well, volume depends on the pressure. Volume depends on the temperature, you know. And so you get more open-ended questions like that. But people aren't used to open-ended questions because they just don't have that much practice, because when you look at this chem book, it's all focused on the right answer, you know, and getting that answer. And so therefore, sometimes I ask an open-ended question, and sometimes when I ask the open-ended question, I get, cannot answer this. You know, cannot answer because not enough information. Or, you know, you didn't tell us this, therefore I can't answer it. Well, I didn't tell you that because I wanted to see where you'd go with the answer for that. And so this is kind of an open-ended question here, which makes it a bit challenging. And so, you know, when you get an open-ended question, you have, you know, a couple of ways or more of dealing with it. One way is, if they ask you an open-ended question like that, but you want to narrow it down to a single answer, then you say, okay, we'll take that question and we're going to assume that the pressure is this, the volume is this, and the temperature is this, and this is what you're going to get for the number of moles, right? Rather than doing, okay, how does it vary, you know, or how does it do this, right? Or the other way of answering open-ended questions is you come up with a mathematical answer in which you have some variables, and then you set the limits of those variables. So for example, you say at one extreme, you're going to get this, at the other extreme, you're going to get this, and it's going to range in between those two extremes. Okay, that's more of the mathematical. So you're answering the question with an equation, basically. An equation that will give the range. All right, and so this is kind of like that. How precisely could you determine the composition of an ethanol-methanol solution by measuring its density in a picnometer? And so I'm going to do a modified version of this because this is kind of a challenging question. How precisely could you determine the composition of an ethanol-methanol solution? And so what we're going to have here is an ethanol-methanol solution. And so this is going to be number 79, and it's going to be a modified version to make it easier, I think, to answer. But we have I'm going to just call it methanol, ethanol, solution. What is the solution again? A homogeneous mixture. So we got a mixture of methanol and ethanol. Right. Could we tell this? We want to know how precisely can we determine the composition. And so what we want to know is what is the percent methanol in this? And what is the percent ethanol in this mixture? By knowing the density. And so basically we have two unknowns, X% methanol, Y% ethanol. And if we're given the density, let's say the density is equal to 0.7905 grams per milliliter. This is the way I'm going to modify it because now you have a target. Now we have the right answer, right? We only have one answer for this. And so here, given a density for the mixture. Okay, the first question is, can we tell just based on the density of this mixture how much methanol and how much ethanol we have? Yes or no? Actually, yes. How can we tell, based on the density, how much ethanol and how much methanol we have? Well, we look here. The density of ethanol was 0.78, what was it again? 94 grams per milliliter. The density of methanol is 0.7914 grams per milliliter. And so this is a case where, you know, what we do is, this brings up a forest analogy that I use a lot. The forest analogy is like this. You know, when you're solving it for one right answer, that's like looking at one tree in the forest. You know, I got the right answer, it's that tree, right? But a lot of questions, they don't want that one tree, they want the whole forest. So tell me about the whole forest, right? You know, what's the extreme end? You know, what's the other extreme, and how does it vary? You know, with regard to elevation, temperature, whatever, moisture. And so here we already see it. At one extreme, if this is pure ethanol, what would its density be? Pure ethanol, no methanol, its density should be that of pure ethanol, 0.7894. If this were pure methanol, then it should have a density of 0.7914. So the two densities are different. And so let me tell you, if there was a 50-50 mix, you know, half ethanol, half methanol, do you know where its density would be? Its density would be right in the middle. And the more methanol you have, the greater the density. The more ethanol you have, the lower its density, because it's going to shift one way or another. And so here we see the ends of the forest, and our tree is somewhere in here, because when you look at our tree, it's 0.7905, which is close to, looks like it's close to methanol, maybe more methanol, I don't know. Do you guys see that? And so this way we can determine the percent composition by looking at the density here, because the density is a composite mix of the two. There are two methods of doing these. Actually, there are more than two methods, but there are two methods that we're going to look at initially of doing multi-variable problems like this. And one of the methods is the system of equations, which we did for the Celsius, Fahrenheit, right? The other method I want to show you now, and that's the graphical method. And in fact, they hint we should use the graphical method because they give us this hint. Assume that the density of the solution is a linear function of the volume percent composition. And so they're telling us that we expect a linear trend in our observations. And so the way we do the graphical method is this. Which of these two has a higher density? Well, methanol has a higher density. And so what I'm going to do is I'm going to have the x-axis vary from 0% methanol to 100% methanol. The reason is because on the y-axis I'm going to plot the density of the mixture. And the density of the mixture, if it's 100% methanol, then the density should be 0.7914 grams per milliliter. If we had 0% methanol, that means it's all what? If we have 0% methanol, it must be 100% ethanol. This should be 0% ethanol over here. If it's 100% ethanol, what's its density? 0.7894 grams per milliliter. Like that. Okay, now we're going to assume it's a linear function, which means what? Which means that it's a straight line trend, right? There's no dramatic increase or dramatic decrease, All of a sudden it just doesn't drop off a cliff or shoot up like a rocket. And so we're going to assume it's linear, which kind of makes sense, doesn't it? Because we're just going to vary the amount of heavier, or not, it's not heavier. Is methanol heavier than ethanol? Methanol is not heavier than ethanol, so why is it more dense? Ethanol is heavier than methanol because we get more efficient packing, which means we get more atoms per unit volume in methanol than we get in ethanol. Well, anyway, this is linear. And so this is what I mean. This is the whole forest right here, the green line. These are the extreme, this is extreme boundary on the left, extreme boundary on the right. And we see the entire forest here. Usually most people don't like plotting. They don't like making plots because it takes so much time graphing things. Actually, not so much time if you use Excel. Using Excel is very rapid, but graphing by hand, do you like graphing by hand? No. But, you know, when we have the whole forest like this, then it's easy to see, you know, at any density between 0.7894 and 0.794, we can figure out the composition based on that. Or at any composition, we could figure out what its density should be. Just get a ruler, right? Do that. But us, we like to represent this graph using a function, mathematical function, which we call it's an empirical equation. Empirical equation is based on what? Theory? Observation. So here are observations. What's the empirical equation for this? Well, it's simple. It's a linear function. Y is equal to mx plus b, where y is the density of the mixture, x is percent methanol. Why did I pick percent methanol rather than percent ethanol? Why didn't I go from 0% ethanol to 100% ethanol? You know, why did I pick methanol? Somebody remind me. I said it once, but
You think it's closer to the density of methanol?
well, that could be one reason, but there was another reason I picked methanol. And the other reason I picked methanol for the x-axis, does somebody have that? Was because methanol had a bigger or higher density. That way, I'm going to get a positive slope versus a negative slope. But it absolutely doesn't matter. You could have picked ethanol here and gotten the same exact answer as if you put methanol. It's just my preference for working with positive slope versus a negative slope. That's the only reason. But either one would have worked. And so figuring out the slope, well, the slope is delta y. Delta y is equal to 0.7914 grams per milliliter minus 0.7894 grams per milliliter. And so that's going to give me 0.0020 grams per milliliter. And then I get my delta x over here. And the delta x is I'm using methanol. So my delta x is going to be equal to x final, 100%, minus x initial, 0%, which gives me 100%. And we have to be careful. What 100% of what? It's not just 100%, it's 100% methanol. I would have get the wrong answer if I put ethanol in there. This is the way I set up the x-axis. And so this is percent methanol. And so the slope, m, is just equal to 0.0020 grams per milliliter divided by 100% methanol. And this equals, how many sig figs is this up here? How many sig figs is this? Yeah. Infinite, we'll just say 100%. And so here, we're going to get 0.000020. Units will be grams per milliliter per percent ethanol. So I'll do grams, milliliters, percent methanol. So let's go ahead and put it into the equation. And so getting all these, y is the density of the mixture, is equal to the slope. The slope is going to be 0.000020 grams per milliliter per percent methanol, times the x variable, which is going to be percent methanol, plus the intercept, which is 0.7894 grams per milliliter. All right, so then I don't have to do graphical analysis. I could just use the equation of this line to solve. And so if I'm given the density of the mixture, I can solve for percent methanol. And so this is actually, you know, when I was saying about answering the question, sometimes you aren't answering it for a specific answer. In this question, did they ask for a specific number? Did they ask for a specific number? What is the percent methanol? No. What did they ask for? They aren't asking me for the composition. They're asking me how precisely could you determine the This is a typical question you get at a seminar. You know, at a seminar, they aren't going to give you a whole bunch of numbers and ask you to do calculations. They're going to tell me, well, how precisely can you determine that? Right? How precisely? And so how precisely could you determine the composition of ethanol-methanol solution by measuring its density with a picnometer? And so what do you know about precision? Tell me, what are they asking about? What pops into your mind when somebody asks you about precision? Sig figs. Usually the easy way to get a lot of sig figs is to pay a lot of money. You buy those high precision instruments, right? The ones that can give you a lot of sig figs. You get those. High tolerance. I don't know. High tolerance, low tolerance. I guess. Whatever. But this is not an instrument, right? And so what the heck are they asking? I know about high precision. I could buy a high precision glassware, high precision instrument. What are they talking about in this sense? Are they talking about reproducibility of measurements? No, they're talking about, as I mentioned, they're talking about sig figs. So what can we say about the sig figs here? How precise are numbers going to be? Is it looking pretty good, precision-wise? Yes? No? Are we looking good for precision? No. Why not? Only 2 sig figs. You know, at the most, it seems as if we're only going to get 2 sig figs worth of precision. Is that really precisely defining the composition? No, it isn't. No, this is more rough. But not only that, well, actually, let's see, because we didn't do the calculation and the mixed rules here. And so let's pick a number. You know, sometimes it's hard to see it based on an equation. So what you do is you just assume a number. And so you just randomly pick a density that falls within the forest here. And so I just picked a random number out of my head, which was 0.7905. 0.7905 lies between the two extremes, right? Is that the number I picked? Okay. And so what we can do is we can just go ahead and put something more concrete down. And so let's say, okay, let's pick a density of the mixture. I'm going to pick 0.7905. grams per milliliter, and let's see how much precision we get from this as far as our percent composition goes. And so we got 0.7905 grams per milliliter. This is equal to, we're going to solve for percent methanol. This is equal to the above. And so the percent methanol, well, first thing is we'll subtract this from both sides. And so if we subtract that from both sides, we're going to get 0.78, actually, it's going to be like this, 0.7905 minus 0.7894. Okay, this is grams per milliliter, this is grams per milliliter, and we end up with 5 minus 1, 4 is 1, 1, 0, 0, 0. 0.0011 grams per milliliter. This is going to equal 0.000020 grams per milliliter per percent methanol times the percent methanol. And so we see, after doing the subtraction, how many sig figs do we have? 2. And then what do? We're going to divide it by this, the slope. And so if we divide it by the slope, I'll just go ahead and write it up here. So I'm going to have 0.0011 grams per milliliter divided by the slope, which is 0.020 grams per milliliter per percent methanol. I'll separate the units here. So the grams per milliliter cancels out, and then I'm dividing by 1 over percent methanol, so you invert and multiply. And so this is going to give me what? Percent methanol. What is it? 55 point what? 55 point. Well, your calculator only shows 55, right? So is it point anything? Yeah, your calculator doesn't show you it, but it's 0.0. I want you to show it to me. You know, if your calculator just shows 55, then it's 55.0, right? At least. And so show me one extra digit. 55.0% methanol, and to the correct number of sig figs, it would be 55% methanol. And then you're showing me the round off step. And so we could only determine the composition to 2 sig figs for the methanol. What about the ethanol? The ethanol, you know, that's, you probably could do that calculation in your head, right? Because there are 2 things, ethanol, methanol, and both have to add up to 100%. And so how much ethanol do we have? 45% ethanol. And so it's 55% methanol, 45% ethanol, and we only got 2 sig figs. And so to answer this question, you know, how precise? Not very precise, because we only get 2 sig figs. But are we always going to get 2 sig figs? It actually could be even worse. Do you see how it could be worse? You know, we got 2 sig figs here in the slope. We got 2 sig figs after the subtraction. How could it be worse than this? This is based on the rules of sig figs. And so we got this as the composition, but this wasn't asked for in this particular problem. This was just to help us visualize, you know, what it is about precision, right? And so sometimes you could do that. Like if you ever get stuck, you know, the question is throwing you for a loop because you need numbers to punch in, then just go ahead and assume numbers. Let's say, let's assume this number and see what we get, right? How could it be worse? Well, it could have been worse if I gave you this density. I'm going to change it. Let's say in the next example, I say the density of the mixture is 0.7900 grams per milliliter. It's the density, 0.7900 grams per milliliter. How many sig figs am I going to get in my composition? I'm only going to get 1 sig fig. Does everybody see that? Why am I only going to get 1 sig fig? Okay, if this is my density, then I have to do the subtraction, the 0.7894, right? So the first step here is 7,900 minus 0.7894. This is 4 sig figs, this is 4 sig figs, but after the subtraction, how many sig figs do I have? 1 sig fig. And so I can figure out the composition to 1 sig fig. Is that very precise? No, not at all. And so the way to answer this is not very, because we're going to have 2 or 1 sig fig for the composition. How can we make this more precise? What do we need in order to precisely determine?
The sig figs of the density picture.
Yes. We need a more expensive pycnometer. A more expensive pycnometer we'd be able to get more sig figs so that we could get the density to more sig figs. And so the more sig figs we have in the density, the less round off error. Think about this. If the density were known for both of these to only 1 sig fig, let's say the density of ethanol, what is the density of ethanol to 1 sig fig? Huh? Not 1. Point 0.8. And the density of methanol to 1 sig fig? 0.8. Do you see round off error occurring? This is round off error. Can you tell the difference? You can't tell the difference. Both look the same to 1 sig fig. And so the higher the precision, the more digits you get here, the more these two are going to be differentiated, the more sig figs we're going to get, and the more precise we'll be able to determine the mixture composition. And so just the opposite effect would happen going the other way. All right, so this is number 79 is definitely a bit different than some of these other ones because we aren't solving for the right answer, the one specific number. Is the correct answer. All right, let's see. Here's some more stuff. The Greater Vancouver Regional District chlorinates. Oh, any questions on this before we leave? You know what? I forgot to do something. I told you there are, different ways you could solve these 2 equations, 2 unknowns. What's the other way? I just solved it using this graphical method. What's another way you could solve this? I'm sorry? It's dimensional analysis plus something. You can't just use dimensional analysis alone. If you use dimensional analysis plus... You could use guess and check. Guess and check works. You could do by estimation, You might, this graphical method, what it should remind you of is the average atomic weight or average atomic mass. Do you remember calculating those for 2 isotopes? This is kind of similar to that. You got 2 extremes for the isotopes. That's for things with just 2 isotopes. Guess and check could work, but the typical way, if you have x and y as unknowns in math, how do you solve for x and y? You solve for x and y using a system of equations. 2 equations, 2 unknowns, right? And so let's set that up. I'm not going to solve it. But there are some people who don't like this graph method and prefer the system of equations method. The system of equations method, I don't like it as much because it's only solving for one specific answer, so you don't really see, you can see the whole forest, but typically we're just solving for one specific insert. So X, let X be equal to the percent methanol. Let's let Y equal the percent ethanol. And so we got to figure out what X and Y are. And so we have two unknowns. We need how many equations? Two equations. So let's derive two equations for this. What's the first equation? But pops in your mind. Uh-huh. X plus Y equals 1? Yeah. X plus Y equals 100%. It's because these are percentages and not decimal form. If it were decimal form, it'd be 1, you know, but we're going to leave it as percent. We want to solve for X and Y, which are the percent composition. And so you wouldn't want, okay, if somebody asks you, how much methanol is in that mixture, you wouldn't say 0.5. You know, 0.5, what are you talking about 0.5? Well, that's the decimal for 50%, right? And so it'd be much easier to say just 50%. Okay, give me another equation. The other equation will give you a hint. Think isotopes and average atomic mass. Anybody remember the average atomic mass equation? Well, let's think about it here. Let's say there are two isotopes, H1 and H2. If it's 100% H2, what is its mass, roughly? 2. If it's 100% H1, what is its mass, roughly? 1, right? If it's 50% H1, 50% H2, what do you think the average mass will be? Maybe I did. The average atomic mass, actually we're covering it in this next chapter. Is equal to, is a weighted average. And so it depends. You know, we're going to have the percent isotope A, we'll just call it isotope A or 1. What should I call it? Isotope, percent isotope 1 over 100, right? So if it's 50% isotope 1, it would be 50 over 100%. The percents cancel. Times the mass of isotope 1. Plus the percent isotope 2 over 100% converted into fraction times the mass of isotope 2, etc. Does this look familiar? You either do fraction here or you convert it to a decimal. What did you, I don't know, I can't remember what Chem 4 did. Did they convert the percentage abundances to decimal or did they leave it as a fraction? to decimal. Okay, we'll leave it as fractions here. Right? How do you convert it into a decimal? You divide by 100, right? And so this is what you do. And so let's say isotope 1 weighs about 1 U. Isotope 2 weighs about 2 U. Right? Hydrogen 1 weighs about 1 AMU, or atomic mass unit. Hydrogen 2 weighs about 2 mass units. That's familiar? If you had 100% H1, then what would the average be? 1. I'm not going to graph this. I could graph this like we did the last problem, but you didn't graph it in Chem 4. If you had 100% H2, what would the average of mass be? 2. If you had 50-50, what would the mass be? 1.5. If you had 25-75, 25 parts H1, 75 parts H2, do you know what the mass would be? 1.75. If it's 75-25, it would be 1.25. Do you see that? This is just a very simple linear relationship like this, where we're going from 1 to 2. Right? At 50%, we're at 1.5. At 3/4, or 75%, we're at 1.75. At 25%, we're at 1.25. Do you see that? This is what I see in my head when I think about this problem. You just visualize it as some trend, as some graph, right? Because in science, what do we do? We're always looking for, you know how much graphing I've done? Huge. Because what do we do in science? We look for patterns and trends. You know, we try to come up with fancy 3D graphs, which look really cool, and try to present the trends in that way, you know. There's all kinds of expensive graphing programs that I used to work with. Now I just work with Excel, you know. But I used to work with all kinds of really nice, really powerful graphing programs. Excel's okay. Excel's made for finance though, so it's not specifically made for science. But you know, it's very powerful and very versatile, so it's still good. So give me another equation for the average density of the mixture. The average density of the mixture, do you see it's the same thing? If it's 100% methanol, then its density is that of methanol. If it's 100% ethanol, then the density is that of ethanol. And then we have a nice linear variation between the two extremes. It's exactly the same problem as average atomic mass. And so what's the other equation? Well, it's exactly the same equation as the average atomic mass. Do you see the connection? A lot of people wouldn't see the connection because, you know, they aren't, you know, it's not drilled into their mind. They haven't, you know, drilled it to the level where all they can do is regurgitate what they've seen for atomic mass, but they can't connect it to anything else, right? The way you can connect it is the repetition. You see it over and over again, and eventually you go, hey, this looks kind of familiar. Hey, I've done this before. I've done this before a lot of times. It's the same thing I was doing earlier in Chem 4. This 2 unknown, you know. Although in Chem 4 you wouldn't have gotten the 2 unknown. In Chem 1A you might get a 2 unknown, an average atomic mass type problem. And so give me another equation. Here. We're rapidly running out of time. But let me just give it to you. The density of the mix is going to equal what percent or what fractional, you know, this is percent methanol, it's over 100. What fraction of this mixture is methanol? And so this would be times the density of methanol. If it's 100%, it's all methanol, and we get 100 over 100 is all methanol. And if it's 100% methanol, how much ethanol do we have? 0. So if we have 0 over 100, it's 0 times the density of ethanol. There's no ethanol in here, it's all methanol, right? If it's 100% ethanol, then this is 0, this term drops out, and this is 100, and we get the density of ethanol. If it's a 50-50 mix, then it's the average of the two. Do you see that? So this is the exact same equation. And using these two equations, now we have a system of equations we solve for x and y. But when we do it this way, you know, we just have one density, the 0.7905 grams per milliliter. So sometimes we aren't seeing the whole forest. I see the whole forest because I know what these mean, you know, visually. And when I see this, I can see plots and that kind of stuff. But maybe, you know, maybe you don't. Maybe you just see one value here and one answer, one x, one y. Does that make sense? Okay, so either way is fine. I don't care how you solve it. You could use system of equations or you could use graphical method. I prefer graphical because it's much faster, I think. Well, let's continue here. Not everything is linear, though. Okay, not everything is linear. So let's look at some nonlinear functions here. Here's a nonlinear function. The following equation can be used to relate the density of liquid water to Celsius temperature in the range 0 to 20 degrees C. So from 0 to 20 degrees C, they get this funky equation. And all that is, what kind of equation is that? That's an empirical equation. In Chem 4, you use this table. It's called the density of water table. You have the temperature, you have the density of water, and you get temperatures like 25, 26. They'll tell you the density of 6 sig figs. Have you seen that table? This is in the first experiment in Chem 4, where you use it. Well, anyway, what if I had 25.3 degrees C? Oh, 25.3 degrees C is not on the table. The table jumps from 25 to 26. And so what should I do? Should I just assume that, oops, this is not 25. Should I just assume that 25.3 is close enough to 25 and use the density entry at 25? Is that the best thing to do? No. What did you guys do in Chem 4? Well, what I have my students do in Chem 4 is do a linear interpolation. The linear interpolation assumes that the variation between 25 and 26 is linear. And we do just what we did in the previous problem. You know, if it's halfway between, then it's the average too. If it's more towards 26, it's more towards 26. So we can figure it out based on an equation like this one, or based on whatever way you want to do it. Do it ratios. I have my students do ratios. We could do a linear interpolation, or we could just graph it. You know, a lot of people will just say, screw that, I'm just going to graph it. They graph it, comes out something like this, let's say, and then they go, okay, at 25, it should be this density, you know, or whatever. But what's better is this is a really weird equation. You know, it peaks out at 4. And it turns out that that weird curve is fit by this. This is a quadratic. You see the square here? And so this is a nonlinear empirical equation. And so, you know, if we're thinking linearly, it doesn't work. So this one's a little bit different in that sense. How late do we go till? Oh, okay. I thought we were going to 15, so I was rushing to finish. But anyway, so we got this nonlinear, and it's just an empirical equation. Does this equation come from theory? No, it's just some mathematical function. And this mathematical function is kind of limited because really we should have one equation that describes the entire density curve for water, right? From theory. But we don't, because now we got this one equation is only valid from 0 to 20 degrees. From after 20 degrees C, it starts to deviate. And so do you remember R squared, what R squared means? It's a statistical fit of what? R squared. R squared is a statistical fit between the empirical equation and the actual experimental observations or data. And so it looks like this equation works good up to 20 degrees C, where the line defined by the equation fits the curve, but after 20 degrees C, there must be some kind of deviation in the data. Otherwise, they would give it a wider operating range. Does that make sense? And so here they're limiting the range because water goes from 0 to 100 degrees C, not 0 to 20 degrees C. So what happens between 20 and 80? Well, this equation must not work. It's R squared must be pretty bad. Otherwise, they'd give it a wider range. Well, anyway, getting back to this, to 4 sig figs determine the density of water at 10 degrees C. So that's just plugging 10 in here. This is simple algebra, I think. B, at what temperature does water have a density of 0.99860 grams per cubic centimeter? So we plug in 0.99860 and hope the temperature is between 0 and 20. If it's between 0 and 20, this equation is valid. And so we plug this in here and then solve for T. How do you solve for T? It's a second order equation. How do you solve for T? Well, you have to use the quadratic formula. We use the quadratic formula a lot in Chem 1B, not so much in Chem 1A. Maybe here once, and then in some other chapters we have to use it. And we have to use some other even fancier techniques to solve some of these problems. In the following ways, show that the density passes through a maximum somewhere in the temperature range to which the equation applies by estimation. Estimation is just guess and check, right? You want to figure out the max. Do you know the maximum? You know, the density of water increases from 0 to, do you know where the max is? About 4 degrees C. And then after 4 degrees C, the density starts to decrease. And so we could just guess and check by plugging in different temperatures and seeing what happens to the curve. You know, just kind of plot it out crudely. By the graphical method, graphical method is, this is guess and check. Graphical method is actually making a nice plot, 2D plot like that. Or by a method based on different, if you've had calculus, then you could just figure out what the maximum of this function is using calculus, which might be the easiest way of doing it. Skip that problem. Okay, this last mixture we did was a mixture of ethanol and methanol. Let's look at this one. 85. A tabulation of data lists the following equation for calculating densities of solutions of naphthalene in benzene. So if we take naphthalene, which is organic, and benzene, which is organic, and make a mixture, then look at how the density varies with the percent naphthalene. Percent naphthalene would be percent N. Is that a linear variation? As the percent naphthalene increases, does the density change linearly? Yes or no? The density does not change linearly. How do I know? Because there's a square in here. If there's a square, there's a cube, any higher order than 1, it's a nonlinear function. Nonlinear functions have funky curves to them, right? And so this is something that doesn't behave like you normally would expect. And so the way we solve the ethanol-methanol would not have worked in a naphthalene-benzene mixture because it doesn't behave in the same way. Why? Why? Well, that's left of theory, but this is the empirical equation describing it, right? Or some hypothesis. All right, some of these others are similar. So we get a little snapshot of some of the techniques that you need in order to solve some of the more challenging problems in the latter chapter. And so this is kind of the introduction to this. If you want, you know, the basics, a refresher of the basics, then work out the homework problems that I gave, or take a look at the, they have some really good review problems in the exercises somewhere. Just a quick review of everything. Let's see, where is that? Here. Somewhere in there. Okay, what I want to do is I need to get into chapter 2. And chapter 2 deals with atoms Did I tell you about that guy I met that gave me his book as an alternative to atoms? That guy didn't believe in atoms. And so that happens. So let's say your friend comes up to you and asks you, do you believe in atoms? Yes or no? Yes. I hope you would say yes after, especially after Chem 4, right? You better say yes. I believe in atoms. Okay, and then what if your friend says, prove it? Or what if this guy approaches you and says, prove it? Or what if you're on some oral examination and somebody says, give me proof that atoms exist, right? And so all I want you to do in the last minutes of the class is this is going to be another pop group practice quiz. You can work with your neighbors, come up with one piece of proof that atoms exist that, you know, I could have used to explain to this guy. Hey, see this? This is evidence here. You know, I'm going to take your book and throw it in the garbage, basically. Or tear it up. No, I need one piece of convincing proof that atoms exist to tell this guy, hey, look, you know, you might want to rethink your theory because I think your theory is wrong. All right? And so, you know, and if this were like a seminar or an oral exam, you got to think, you know, it's silent. You know, and a lot of people think, oh, give me 5 minutes. But can you imagine 5 minutes of dead silence in a seminar? You're thinking about the answer. You know, everybody's waiting for it, and the seconds are like ticking by. Tick, tick, tick. Everybody's waiting for that answer, and they're getting less and less patient. You know, and so you can add some pressure to this. You know, give yourself a couple of minutes, and give me your proof. Or we still have what, 4 minutes left? And so go ahead and use up the 4 minutes if you want, or just give me 1 minute and then hand in. I'd like you to hand this in. I'm going to take this as attendance as well.